Great to see you here again. My name is Luc de Ceuster, founder of the Ceuster Academy, and thank you for visiting my YouTube channel. When you're here for the first time or you didn't subscribe to the channel yet, this is the moment to click the subscribe button and subscribe to the Ceuster Academy's YouTube channel. Do not forget to click the bell button so every time we have a new video, YouTube will inform you. But let's have a look at this video. In this video, I'm going to explain to you the principles of the RSA encryption system. The RSA encryption system was developed by three people: Rives Ron, Shamir Adi, and Adelman Lennart. These three people created an encryption system that is based on prime numbers and modular exponentiation. So basically what we're going to do is to select a power and two primes, P and Q. And we have to select those three numbers in a way that the GCD of the power and the product of the two primes, each reduced by 1, is in fact or has a GCD of 1. Basically that E and the product of those two numbers are relatively prime. Let's have a look how this system works, and we will do some exercises how to encrypt and how to decrypt messages using this system. The RSA encryption system starts with selecting the exponent and two primes P and Q in such a way that the GCD of E and the product of P minus 1, Q minus 1 is equal to 1. It means that those two numbers are relatively prime. Also we have N, which is the modulus for the exponentiation, which is equal to the product of those two prime numbers. And the formula to encrypt any number, any text, is in fact C is equal to M to the power E modulus M. And M we obtain from the letter codes. For example, A, B would give me 0001. That would be M. Now, what is important, first of all, we have to verify if those rules are valid. Let's say we selected for the exponent the number 11, P is 53, Q is 59, both are prime numbers, and we can calculate N, which is 53 times 59, which gives us 3,127, and N is between 2,525 and 252,525. That relates to the system that those gentlemen developed. So basically what we now have to do is to calculate P minus 1 times Q minus 1, which is 52 times 59, and it gives us a result of 3016. Now we have to see if 3016 and 11 are relatively prime. Why is this important? Well, in order to decrypt a message, we have to do the inverse calculation, and we have to find the inverse of E modulus 3016, 11 modulus 3016. That's only valid when 11 and 3016 are relatively prime. Let's have a look at that if it is true. So I can say that 3016 is 274 times 11 plus 2, so we can say that 11 is 5 times 2 plus 1, which means that the GCD is equal to 1. So basically we can use the RSA encryption system with these numbers, and that's what we're going to do in the next step. Based on the definitions and the selections we made before, we can rewrite the encryption formula, which is C, the encryption, the encrypted number that we will receive is M the number to encrypt to the power 11 modulus 3126. Now the word we're going to encrypt is the word live. So the first thing we do is to replace these numbers or these letters by a number. We did that before. We used the classical 26-letter alphabet, all in capital letters, no difference between capital and small letters. So it gives us 11 for L. We have I, which gives us 08. We always use the two numbers. V is 21 and C is 04. So basically we have two numbers here to encrypt, which are 1108 and 2104. And now we are going to apply the formula. So let's call this M1, and we find C1 is M1 to the power 11 modulus 3126. And you can do that in different ways. You can use a website to do this. You can use the modular exponentiation that can be done. Anyway, I did the calculation for you. You can verify this for yourself. And we find that is 2,800 and I have to verify 95. So basically that's the first number. We can take out the comma because this has no sense here anymore. C2 is M2, which is this code here, to the power 11 modulus 3126. And we find here that it's 2104 to the power 11 modulus 3126 is in fact 2126. And based on this we can say that the coded message is 28952126. So basically this has been coded into this series of numbers. This is almost impossible to crack. With these numbers that we have here, it's not so difficult. But when we use large prime numbers, when we use large powers, this becomes really difficult to crack, basically impossible with the means that are available now. Anyway, any code can be cracked, but the thing is that by the time a code will be cracked, it's not relevant anymore. And people change the keys from time to time, so you keep the security going. Of course, today I've read some things about quantum computing, and the expectation is that quantum computing can change things related to encryption. But we don't know for sure yet. We will see how the evolution will go. But let's now have a look how we can decrypt this message. Let's now look at an encrypted message that we received, and the encrypted message is 1683-0150-0798-0810. Basically, we want to know what was the real message, the clear message that was sent to us. Now, we know the key. We know that the key is 13, the exponent, and n, the product of the two prime numbers, 2537, with p equal to 59 and q equal to 43. We also know that p minus 1 times q minus 1 is 58 times 42, which is 2436. Now, the first thing to see is the GCD of 13 and 2436, is it equal to 1? Because we have to know the modular inverse of 13 modulus 2436 to be able to decrypt the message. Now let's have a look at this GCD. So we can say that 2436 is equal to 187 times 13 plus 5. Now we can say that 13 is 2 times 5 plus 3, and 5 is 1 times 3 plus 2, and finally we find that we have 3 is 1 times 2 plus 1, which means that the GCD is equal to this. Now we have to calculate this in the other direction. We have to find the calculations in the other direction, and we start from here. So we have 1 is equal to 3 minus 2. So we have 3 minus 2, that's the first step that we have. Now we put 2 in there, and we know, and I will put it on this side, we know that 2 is equal to 5 minus 3. So when we put it in here, we can say that 1 is equal to 3 minus 5 minus 3. So we have 2 times 3 minus 5, which is still correct. We can verify that easily. Now we have to replace 3. And 3 is equal to 13 minus 2 times 5. We bring that value in here again. So we say 1, we have 2. So we have 3 times 5. We bring 2 in here. So we have 2 times 13. 2 times 13 minus 4 times 5 minus 5, 5 times 5. And the last step, where we will find the inverse, we use this last formula. We can say that 2436 minus 18 times 13 is 5. So basically, I replace 5 in here. So we have 2 times 13 minus 5 times 5. So I have 187 here, 5 times 187, which is 935 plus 2, 937 times 13 minus 5 times 2436, and this number is the inverse of E modulus 2436, and that's what we're going to use to decrypt the message. Let's do that when I clean this board. We found the modular inverse of 13 modulus 2436, which is in fact 937, which gives us the decryption formula to be equal to C to the power of 937 modulus 2537. What we remain to do is to decrypt this number. So basically we can say that M1, the first set of 4 letters, is 1683 to the power 937 modulus 2537, which gets you 2414, which is Y and U. O. Then we have M2, which is equal to 0150 to the power 937 modulus 2537, which gives us 2019, which is U and T. Then we have M3, the third one is 0798 to the power of 937 modulus 2537, and that gives us 2001, and it gives us the letters U and B. And M4 is 0, 810 to the power 937 modulus 2537, which gives us 0, 423, which is E and X. Now when we look at this and we write this message again, we find that is U tube, and there is an X at the end. An X we added just to see that we have basically numbers which represents 2 characters. So that's the RSA encryption system. Basically unbreakable, but like I said, new technologies evolve, other possibilities are there. What will quantum computing do? It will be, or it can be, a game changer, we don't know yet, but there are some expectations that it will. Anyway, new technologies will be created, but RSA up till today is a very secure way to encrypt and share confidential messages. Of course, we have to select numbers that are big enough, large prime numbers, because that makes it basically unbreakable. That's about the RSA encryption. The only problem that exists with RSA encryption is that you have to share a key. Both parties have to know the keys, and today we may have communications with many people we don't know at the beginning. So we have to see how can we facilitate the exchange of keys even over a public network without being compromised. But that we will look into in the next videos. Anyway, this is the end of this video. Do not forget to have a quick look below the video. You will find a lot of links to our courses, great coupons with great discounts. Anyway, there are a lot of interesting topics that you can learn at the Ceuster Academy. And of course, do not forget to click the subscribe button, click on the bell button, and every time we have a new video, you will be informed by YouTube. Thank you very much, and bye-bye.